to invite him to the stage, and I have. So thank you, Haris, for coming. And did I manage to invite you? I did. But there you go. Good. Haris, we have a
Hi, Dr. Laird. How are you today?
good. I'm expecting, I've invited three people I know physically. Uh, uh, oh, wait a second. So I see your, oh, now I see captions. Oh, that's terrible. I don't want captions. How do I stop captions? Yikes, I don't want captions. How do I do that? Uh, there's got to be some way to stop captions. Oh, boy, that's going to annoy me. Okay, well, I'll ask somebody when they come. Uh, uh, so hold on, I have to communicate uh, with somebody who I've invited but hasn't figured his way in. I'm in small steps and giant leaps. So that I've invited a friend that he's not having been in Clubhouse before. He's trying to figure out how to get in, uh, and so I don't want to be talking to him. I want to be talking to you. Uh, but he hopefully, but uh,
Take your
uh,
time.
uh, but uh, the person who's trying to get in is a friend of a friend and has been told uh, that he's a very smart person. So hopefully he'll find his way in, even if he's never been here before. Uh, so okay. So uh, I've invited three people who know me personally, and we'll see if any of them come. One of them is named. Oh, I think I think he just showed up. I think that's. I think Owl is my friend, uh, who we'll call Owl rather than reveal his actual identity. Uh, and, and Owl has asked himself to be invited to the stage, so I'll do that. And this is his first time on the stage. Uh, and so Haris, uh, uh, I want to introduce you to our Owl. Uh, by, by way of doing that, Haris, would you ask me a question so Owl can understand how this thing works? Would you do
Sure.
that
Hi,
for me?
all.
Thank you.
I usually come every week and try to have a question for the weekend. Uh, for this week, I remember it was a few years ago, the European Space Agency had sent out a probe to land on a comet that was going by, and it was able to keep up with the comet going something like 140,000 miles an hour. And it
Hmm.
was rated as the fastest object, man-made object ever to move through space. And and I'm dead curious, how does that happen? Like in space, how does some like what is it? Like, what are the physics involved in that? This probe was able to catch up with it and track
Right.
it.
Well, that actually is a good question. Uh, uh, you still haven't, Haris, you still haven't managed to ask one dumb question yet, but we're still hoping. But that's not one of them. So, so, but because the thing is that what you the thing you need to know about everything in space is that it's following a trajectory determined by the gravitational influence of everything else in the universe. Except in this case, the only thing really of merit is the sun. The rest of the planets have very little anything to do with it. So what that spaceship is in a trajectory, but now I'm going to call it an orbit. And now that I've called it an orbit, I can now appeal to a man named Kessler, who lived around 1600, who came up with Kepler's three laws of motion, and one of them is all objects in the solar system, all or in the universe, in a two-body problem, which in this case is the spaceship and the sun, follow a one of three possible orbits. One is a hyperbola, which is only good if you're coming from another star. parabolas, which is a special case of neither a hyperbola nor an ellipse, or an ellipse. So guess what? We launch every time we stop the rocket engines in a rocket that has left the Earth's vicinity and is now influenced entirely by the sun. It's in an ellipse. Now the comet is also in an elliptical orbit around the sun. So guess what you have to do? You have to match orbits. Once you've done that, you can you can spend all day, all month, all year. You can spend millennia right there. Nothing's going to change. The best you can do is land on the comet and have a good time jumping off the comet and seeing if you can achieve escape velocity at the surface of the comet. In the case of that comet, which I think was 67P, I believe, you could jump off of it easily and never come back. But when you ask the question, how do we match uh, velocities? And the answer is you just keep firing your rocket engines in such a way that eventually you're in the same place at the same time with the same velocity vector, all which is done with these, you know, uh, vernier rocket engines, and you eventually match it and you stay where you are. Did I answer that question?
Pretty much. So once it kind of caught up with it, like it got like what like pulled into its gravitational pull, and that's
Well,
I was
no,
able
okay, but
to keep
now
up with
now
it.
you've got a little problem, okay?
Okay.
Now you've got a problem. You are traveling with the comet, but you want to go into orbit around the comet, but you can't. But you can't because there's not enough gravity,
Okay.
right? The comet doesn't have enough gravity to keep you in a proper orbit. So you have to be doing quite a lot of work to sort of stay where you want to be around the comet. You can be traveling alongside of it, but if you want to orbit the comet itself, you literally have to be, from time to time firing your rocket engines to keep yourself on course because the thing's not round. There is some gravity, and you can stay close.
Okay.
Uh, but but it doesn't pull you into a circular or elliptical orbit. You have to, from time to time, change your engines so that yes, you're traveling with
Okay.
it, but you also are traveling at a slightly different speed than it in order to sort of make your way around it.
Because
Because
it
it does have
eventually
gravity, but
landed
not enough.
on it,
What?
not in a good spot, but it did land on it, which was, I believe, the probe's objective. Oh,
Right.
so okay, because I'm glad I asked the question because this whole time I kind of thought like it was the comet kind of dragging the probe into its velocity, but it really was a matter of the design of the engines that really helped
It matched
get it
orbits,
there.
and then the little gravity of the comet itself was able to have an influence on the spacecraft itself.
Gotcha.
That occasionally they needed to correct the orbit, and so it kind of traveled in a square orbit, a little bit to the right, and then turn left and go down, just to because you don't want to give it so much energy that you can escape the comet's gravity. You want to stay with the comet's gravity at all times, but you also want to have a lateral speed so you don't fall into the comet.
Gotcha, gotcha.
And when what they did eventually is they launched a probe that was designed uh, to land on the surface and stick and sort of tell them things about the surface that it was designed to do. But the problem was that it didn't stick when it fell to the surface of the comet, and it bounced. Uh, and they, since they didn't have high-tech equipment up there to see it as it bounced, they were only able to find the bouncy probe because it took pictures of its surroundings, and then they looked from above to see what on the comet matched the pictures that the probe had taken. So it took them, I think, something like 6 months to find where the probe had found where it had landed. And by that time, the probe had run out of
Right, right, right. I
steam.
remember that.
So,
Right.
but they could still communicate with it because it was run entirely on batteries. There was no, oh, or maybe it was supposed to have, uh, photo cells, but I think it landed in the shadow of a
Right,
boulder,
right,
and
right.
so it didn't have any ability except the batteries that it came with.
And did
Uh,
you know how big? Because I don't think I've asked this. Like how? I know comets come in different size, but like how big is a comet generally? Like, because I think like relative to the size
well,
of
there's no
of Earth.
general, but this one was about the size of Manhattan Island. No, the size, I've seen a picture of it hanging over downtown Manhattan. Uh, so I think it's about the size of lower part of Manhattan Island,
Oh,
which
so this is
is
a
where I
really
live.
tiny thing.
Well,
Wow.
it's not too tiny. If it hit the Earth, you'd be dead, no matter where, no matter where you were. You know, it
I've
would
always
be
imagined comets as like big, like you know, not not moon size, but I've always imagined them being rather
anything
sizable.
above a kilometer or so. I'm not exactly sure on this number, but is pretty much a an extinction level event of the order
Oh,
of the thing that
right.
wiped out the dinosaurs.
That's very fair. That is very fair.
Yeah.
Wow, so it's always amazed me how we can design technology to land on such incredibly tiny things just out there, and
Well,
like
the
I was
answer
really
to
impressed
how
with
we
that.
can do that is you have no idea how smart people can be, especially when they're combined with other smart people with a project. Now, I happen to know that Owl over there is one of those very smart people currently. And by the way, if anybody is interested, I could ask him at some point to describe his credentials because he's currently unemployed. And so, Al, would you introduce yourself? Press the little button on the right where the microphone is so you can speak. There
Oh,
you go.
well, hi, yeah. I'm go by Owl on here. I mean, I don't actually mind. My name is James, but like, yeah, it probably is more convenient to just call me that because that's my screen name here. Um, I mean, I don't know. I'm kind of
I,
a
so I
random.
invited you to come and ask a question
Yeah,
of whatever you can come up with. However, uh,
and this is stupid questions, right?
there you go.
Okay, so everybody always talks about the universe expanding and like you know, that space itself is expanding. Is there
Right.
any difference than to say for that than to say that everything is shrinking and staying in place, and
Uh,
like the forces strengths are
in,
also
in, in
proportionately
other words,
shrinking?
instead of the universe expanding, uh, 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 the idea is that from another point of view, from the point of view of the universe, everything
Every
is shrinking
uh-huh.
so
That's
that things get further away.
yeah.
Uh, I'm having a hard time getting my head around that.
So
Uh,
like oh, go on.
well, no, I essentially, we normally experience it from the point of view of standing on the ground looking outwards. But
Mhm.
you're sort of saying, well, what happens if I was the universe instead of the objects in it?
Exactly.
And so if what I feel is if the universe, if I was shrinking because things in my grasp were somehow moving further away, I'm trying to picture it. I mean, as a turn on the idea of expansion, contraction. It's an interesting flip. I don't know if it works, but it's certainly novel to say the least. Uh,
It,
and maybe there's some way of thinking of it that way, but I can't quite get it. It's
So
cute.
the kind of visual analogy that I have in my head is like, it's always the things that are the same size, or like, you've got the objects that are on the expanding balloon, and like the objects themselves, uh, you know, s- stay the same size. But I kind of think, I mean, I guess if it's like the analogy sort of breaks down. It's not as clean, but like if you
Yeah.
replace the balloon with a bowling ball that stays the same, and you have a whole bunch of little deflating things on them that are all going, boo, and they're also kind of like losing power as they deflate, which is kind of like how I'm saying like the speed of light is slowing down and all that too. Like everything's kind of running out of steam instead of everything getting further apart. But that's as
So
far as it
I'm
goes.
trying to see the bowling ball. So I see. So we start out with a bowling ball with dots on it everywhere, right? But then I still can't get the image of this shrinking. So so the bowling ball itself shrinks
No, the
and
bowling.
leaves the stars behind.
I think the
So,
bowling ball stays the same, and when I meant like a non-shrinking sphere or a non-expanding sphere, but all the things on it are shrinking rather than the things on it staying the same, and the sphere is expanding.
uh-huh.
Yeah,
Does
but
does anybody else, can anybody see what he's saying? I mean, uh, I can't quite, I feel that there's merit there, uh, but I can't see it quite, you know? It is an inversion and therefore reasonable to examine. I just can't see it as a, because every single time the universe gets brought up in a conversation, it's always on a balloon that's being blown up. You
yeah,
know, it's always that, or either that, or it's a raisin bread. And nobody ever talks about shrinking. This is the first time we have a fan of a shrinking universe here with a reasoning by analogy. You know, perhaps the opposite is true than what we see, we
I
feel.
guess he's not saying the universe is shrinking. The universe is staying the same as is, but the objects inside the universe are shrinking, giving you a feeling that the universe is expanding.
yeah.
Right, that's what he's saying. But can you see what he's saying? Like,
Yeah.
you don't mean, he doesn't mean stars shrinking,
Oh,
and eh,
a bunch of deflating balloons in a room that stays the same size.
okay. But then is each balloon that's deflating a star or galaxy, or what is the analogy with a deflating balloon? That's what I'm
Well, there
trying to
would be
get.
some kind of like weakly bound way that they would be stuck together as far as like the gravitational way, the same way that the objects on the balloon that's getting bigger are like rigid and therefore don't expand because they're only stuck to the balloon at one place, or like maybe they're smeared onto the balloon with a sticky goop, but their forces that hold them together are stronger than the forces between them and the goop, so they stay the same size while the universe expands on the balloon is the normal way, kind of, I think.
Oh,
So I guess something that is static would have to be replaced with something that's elastic and deflating. You just flip which things are elastic and which things are static, and then you have them deflate. And they're still stuck together somehow, like a whole bunch of balloons stuck together with goop on a bowling ball as they deflate individually, but they're kind of sticky to each other, so they kind of schwump with each other as well if they're close enough together. I don't know.
I don't know. I don't know. I'm still having trouble with it, but it's novel. It's certainly worth certainly worth the brain power to pull it off. Uh, uh, so, so Al has. I've asked him to come here and ask me something hard, and instead he's come here and offered me something impossible. So I do appreciate it. Right,
There you go.
right. Uh, so, by the way, I'm also demonstrating the room to Al because one of the things that Al, or I'm going to call him James because that's his name.
Yeah, that's cool.
One of the things that James and I are talking about is how to take this room, which, by the way, is much smaller at this time of night than it normally is. Usually, at this time, we have about, I'd say, twice as many people as this. And by the end of the evening, which is 2 hours from now, we might have uh, maybe 30 people listening. Uh, for instance, Dash just came, and he's normal. He comes often. And uh, uh, and at least that. I'm having a little trouble with my screen here, so I can. Anyway, so the idea was that James would suggest a way that this room, which is audio only, and I can talk to each of you, and you can talk back to me, and you can ask me questions, and I can interact with you. If we did the same sort of thing in Twitch, in YouTube, all sorts of other things where I would be live, you all would be typing at me. There is nothing in the internet, as far as I know, where you all can be talking to me, except in Zoom. But Zoom doesn't have anything like this Clubhouse thing going on. In other words, we have a Zoom session. You've all been invited individually, and we all make an appointment, and we all get together. And this is not like Clubhouse. Is random people from the universe can show up here. Anybody who has a Clubhouse app can show up here. Whereas in Zoom, if you have the Zoom app, you can't show up where I'm having my doing my thing. So what James is trying to think out is how to link Clubhouse, for example, with YouTube Live, where perhaps the people I would be talking on YouTube at the same time I'd be talking in Clubhouse. And the people I would be talking to on YouTube Live would be the people who, in fact, are talking to me on Clubhouse. So we would have sound from other people on YouTube while at the same time getting the audience from Clubhouse. That's kind of like the thing that James is trying to think out. As I said, he's a very smart boy. But I don't think you're going to succeed, James. This is hard. But I invite you to try. And I invite anyone uh, in this room who is still listening. We have more people. Invite anybody to try to help you. By There's a chat in the lower left-hand corner which people can type into, and so share with everybody. And Clubhouse used to have the ability to individually talk to other people, and I'm not sure if that's a possibility that we can still do. But if anybody wants to try to talk to James, who's now out there as Owl, uh, try to figure it out if you need to do that. In the meantime, what I have done is put up something I've never done before in all the 3 years I've been doing this on Clubhouse. Is I put up a link to one of my favorite people, and one of the things that she has taught me recently that I think is really cool, and I thought that at some point we might discuss that if we run out of questions that people ask me. And so that does happen because in Clubhouse increasingly people are here to listen but not ask, and because many of you uh, have been here on the stage before, and have shot your bolt, and now you're here to see what happens next. So, but in the meantime, Abi, Ab, Abi, how do you say your name?
Abhi, yeah.
Yeah, Abi, can you help me with a question?
Yeah, sure.
Good.
Sure, Dr. Late. So the question that I have is regarding the probes that are being sent out to the other planets, right? So they should be traveling for months or years together sometimes, and
Right.
how they're being steered in one particular direction, or how their thrusters are being fired when there is no space is actually entirely empty. It is having
Right.
very sparsely populated air molecules here and there, but it is
Right.
like largely empty. So how they're going to burn the fuel that they're carrying for changing the direction, or when there is lack of oxygen.
Well, they carry the fuel with them, and they carry two types of fuel. Mostly, uh, after they've gotten off the Earth, they carry mostly what's known as hypergolic fuel. And the nice thing about hypergolic fuel is that if you put the 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 A test tube and the B test tube together, and you combine them, they immediately explode. If you do it in such a way that you can control the explosion, you get thrust. So you don't need, quote, an oxidizer per se, although one of them is probably an oxidizer. And but but you do, but they carry the components which can be used to uh, thrust it. I have this little idea that you are operating with the same misconception that the New York Times operated on in 1936, where Robert Goddard, who created the first liquid fuel rocket in the history of mankind, uh, he uh, his idea was that he could use this rocket to go to the moon, by going into outer space. But of course, everybody knew at that point, even then, that outer space is a vacuum.
Mhm.
So the New York Times reported that it wouldn't work because outer space is a vacuum and there's nothing to push against, right?
Right.
And that I wonder how close to that mistake you just made.
No, it's just a question. I know that for sure. It's a fact that for a fact that it is working, but I just want to know how it is working. So I didn't question the technology, but I just want to understand how it is working. That's
How
it.
is it working? Well, Alder, who happens to be here, is an expert in this sort of thing. See, I'm just an astronomer, whereas Alder wants to create a spacefaring civilization, and he's also the among the originators of the Small Steps and Giant Leaps house, originally club, and now uh, how now house. So Alder, could you answer his question?
Hi, Laird.
Right.
I just hopped in. What was the question again?
Uh, well, he was kind of curious how rockets make their way around the interplanetary space, given that there's no oxygen in outer space for them. And I didn't know how he finished that sentence. I was thinking push against, but no, he was thinking, well, Abby, can you say it again, please?
Yeah. So how the thrust is being generated by burning the fuel when there is no oxygen to burn it.
Right. And first,
Well,
and the first thing I said was, is he making the same mistake that New York Times made when they said that that Goddard's spaceship wouldn't work because there's nothing to push against? But I think that's not his problem. I think it's different.
so you are pushing against, you're pushing against your own exhaust. You're pushing against a variety of things. If you're doing if you got something like, let's say, an ion thruster, you're getting energy in order to move forward just by the ions shooting out the back of your spacecraft. If you're doing something like a good old Orion drive, you're riding a wave of a nuclear explosion. Just because it's a vacuum doesn't mean that, like, everything that enters the vacuum loses all of its mass and the ability for you to push against it. So.
Abi, does that answer your question, or are we not getting quite to what you're trying to ask?
No, I think no. I got the answer. Sorry,
You did.
excuse me. I got the answer. Yeah.
Good. Good.
Thank
Right. But because it would have been so much better if you were making the mistake that they made many years ago, which is a mistake uh, that uh, Aristotle made, and then Newton sort of figured out that Aristotle was wrong and corrected it, but the New York Times didn't get the message because the New York Times thought that as soon as you get into outer space, you have nothing to push against, so you can't get anywhere. And that turns out to be stupid. But, if you will, the entire history of mankind was also stupid. They believed, like Aristotle, was that an object in motion doesn't continue in motion unless you keep pushing on it. Because Aristotle was not under he hadn't figured out there was this thing called friction, which sort of stops you. But in the outer space, there's no friction,
you.
so nothing stops you. But Newton uh, gave us Newton's laws of motion, which among them, and these laws cannot be broken. The rules of the Ten Commandments can be, but these cannot. These three cannot be broken under any circumstances, except if you happen to be talking to Einstein. But otherwise, uh, and even there, an object in motion continues in motion in a straight line unless acted upon by an external force, is his second law of motion. And that's where Aristotle got wrong because he thought you had to push. And he didn't understand that friction was the force that slowed it down. Uh, so, so, and then of course, the the other thing that Einstein threw into the equation was, see, Newton said in a straight line, but in fact, what he meant to say is following a geodesic. See, because uh, objects in outer space in orbit are really just trying to be in a straight line, but straight lines uh, uh, under the influence of mass turn out to be curved. Uh, and so the straight lines uh, of the universe are really just the curvature of space. Uh, I didn't need to go there, but I did. Okay.
I mean, is it not the celestial objects trying to get tidally locked against the Newton's first law?
Say it again.
So the celestial objects, say for example, moon and the earth.
Okay.
So millions of years back, they are not tidally. Millions of years back, they were not tidally locked.
Oh no, they've
But right
always been
now, they
told.
achieve this tidal lock. So without
Yeah.
having any external influence. So how that happened? Is it not against the Newton's first law?
I'm sorry. The title stuff is really kind of more complicated. See, all the laws of Newton refer to basically point sources. Okay, so you're talking about things microscopic in size, but whatever. So the Earth is microscopic, but has the mass of the Earth. The Moon is microscopic, but has the mass of the Moon. As soon as you introduce the nasty business of it having size, you introduce the fact that some parts of the Earth are closer to the Moon than others, and some parts of the Moon are closer to the Earth than others. So you start to mess around with Newton's stuff because you now have to do something called integral calculus to add it all up. Integral calculus is the mathematics of adding up all the forces involved. And if you do that, you end up with tidal forces.
Hmm.
Uh, so I'm not sure exactly what you were saying in the first place.
No, I say, no. You said that Newton's laws cannot be amended. So my
No, no,
question
no,
was
they
how it
can't.
was.
But
Yeah.
but they can be used to concoct more complicated structures, like objects that have physical size.
Mhm.
So essentially, every particle of the Earth has a certain amount of gravity,
Mhm.
right? So
Right.
you have to add up the mass and the position of each particle of the Earth, and its velocity. So you add in the three velocity components, mass and everything else you might need, and throw it all into the equations, and you come up with something like tidal forces, which of course is unnecessary. You can simply say that the part of the Earth is closest to the Moon and the part of the Moon that's closest to the Earth exert extraordinary forces on one another,
Okay.
and so
And
that's
hence the bulge. It's
hence
not
the
a.
bulge.
Yeah. Okay. Got it. Yeah.
Right. You don't have to go to this integral calculus to get there with an understanding of what's going on. But
Mhm.
it is interesting that you do need a little bit of help because the other bulge on the other side of the Earth, if you will, goes in the opposite direction away from the moon. So there's nothing. So the moon's force is the least there. So therefore, it holds the tides the least. So it bulges away. That's harder to understand.
Mhm. Yeah.
I definitely agree with that. Yeah. Uh, and I have a friend. So the other friend I have in the room today is Trudy. She's also new. She's never been here before, and she has no particular interest in astronomy. Uh, but I've known her for 40, 50 years. And so I would just invite you, Trudy, to speak if you care to. I've just done that, and if you want to, you can. But for that matter, anybody else in the room, for example, Trudy, you should meet Z. Z has been in my room since day one, and she is a big fan. What she does often is she listens to me to go to sleep. I put her to sleep on a regular basis, although she hasn't been around that often recently. Uh, and so I have a few people who have been around. But what I do need in the room is people asking questions, and not just uh, people coming by to say hi. So let's see if John has a question.
Hi, Dr. Laird. Thank you very much. Uh, I have a question. Actually, see, lots of times we read the science fiction novels. They also they always mention the nuclear powered spaceship.
Nuclear power spaceship. Okay.
Yeah, I'm just wondering how could that happen? See, like a nuclear powered spaceship. If you have, see, for example, if you have, see, nuclear power, or see, either fusion or fission, you generate a lot of energy.
Right.
But this energy has to, see, push something
Yes.
to, see, like to, that means you always have to lose something, right? See, like
Yes.
you push down metal,
Yes.
gas, or liquid or whatever stuff.
Uh-huh.
So your, see, like so your actually is very limited. So
Yes.
you push, as you push out more, and then you actually you lose a lot. You lose more and more till, see, you don't have anything to lose. Maybe
Yes.
you can, you can lose your structure of your spaceship.
Right. Okay. So basically, John, you've just explained why we are not going to make it to the nearest star anytime soon. Uh, because whether you use nuclear fusion, nuclear fission, or antimatter matter annihilation, you still are going to run, and because you have to push something out the rear end of the thing, okay? So the question is one maybe of efficiency, and at 100% efficiency, which I'll explain in a second, you still are left with the fact that you're using up your fuel. So it uh, there is a limit. So to how fast you can go, uh, given the amount of mass that you start out with, if you even if you annihilate it all, it doesn't get you up to light speed. It doesn't get you anywhere near there. So let's start with uh, uh, a nuclear fission. What you do in a normal spaceship, and Older, correct me if I. Oh, he's on a phone. Cool. Uh, uh, so uh, normal rockets, they combine two things. They create a very high temperature. That temperature expands the gases. The gases leave the rocket nozzle at a particular velocity, and something known as a specific impulse, I believe, uh, not my field, rocket engines, and uh, and and then on the basis of the specific impulse, you can get a certain amount of thrust out the rear end of the thing. Uh, if you use nuclear energy, you can create a much higher temperature, and therefore you still have to throw something at the rear. It can be anything you bring along, washing machines, dryers, water, anything you want, but it has to be thrown out at extremely high velocities based upon the temperature that you've heated it out at to create the thrust. If that's with nuclear fission, with nuclear fusion, you can get even higher temperatures out of the deal. But of course, who knows how to do that? And then throw that out the rear end, and you can get even better specific impulse. But nobody knows how to build a fusion engine. Believe me, that's nobody's got even close to that. We haven't built it on the Earth, at all, uh, uh, except in the worst possible way. Uh, but nuclear fission engines are real, and they are planning to. We have launched them, I think, in the past. Maybe not, but certainly we are planning to launch them in the near future, and they will serve to have a higher specific impulse and be able to get us to uh, uh, the nearest places we're going with a smaller expenditure of fuel, and therefore we'll be able to get there faster or with bigger payloads. Either one you choose. Uh, and then the last thing is nuclear is matter antimatter. If you uh, annihilate matter and antimatter together, the result is a is light rays, gamma rays, And gamma rays have, by their very nature, a momentum, and they can impart that momentum to the object, and you get yourself uh, a the best possible engine you can get, which is antimatter. But that still doesn't. We don't know how to do that. So I didn't know if I answered your question, did I?
Yes, yeah, actually, you did it. So I think that's almost impossible to use nuclear power to uh, power the sea, like the way that we saw it on Earth. Because on Earth we have air, we have all this water vapor, and then we have endless supplies surrounding the nuclear generator, so we
Right.
can push things out. But in space, we just cannot. So that's why when I read those novels, you just kind of thinking about it. How could
You,
this happen?
you have to wave your hands. There's no way that you can actually the best one I've ever seen, the best way I've ever seen them talk a good talk uh, is uh, uh, Haris. What's the name of that novel about that was written by the guy who did The Martian? Uh, uh, it's or Lois. Uh, the
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 novel about the Martians.
Yeah, I always forget the oh, it's called Hail Mary.
Okay, yeah, yeah, yeah.
In Hail Mary, which is the best, as far as I'm concerned, best novel I've read almost ever, uh, uh, because I like the science in it. I like that it's. You remember uh, uh, the the Martian guy on, done by Matt Damon, not Matt Damon, but the actor. He said we're going to do the science the shit out of it. Well, this guy uh, in this novel sciences the shit out of saving humanity, but in the process, uh, he has figured out how to power a spaceship to get to the nearest star in his lifetime. And so you really have to go, if you want the best rocket engine that anyone can ever invent in science fiction, you got to go to Hail Mary and check out that rocket engine. That's the best one I think that's conceivably possible. And it does have a lot of matter antimatter type stuff going on. So check that one out. Uh, but the thing is, if you're on Earth, you don't need a rocket engine which carries the oxygen with you. You can if you're on the Earth, you can ride a jet plane and the oxygen's there for the taking. So all you got to do is bring the fuel. But if you're going into outer space, you need to bring both the oxygen and the fuel to burn with you. So it doesn't get you as far. And you have to go much faster than a jet plane to get to where you're going because space is awfully big. So you kind of use it up very quickly. Uh, so Elon Musk's giant spaceship uh, is all well and good, but it ends up traveling at 7 miles per second uh, instead of the speed that jetliners travel at, which is, a mile every few minutes. Anyway, so whatever I said. Uh, uh, so we have on the stage also two people I know, uh, Dash and Z, who calls herself Z, but she's Lois. Uh, and so Dash, you're next if you want to talk.
Hey, Dr. Laird, how are you, man?
I'm good.
So, um, I just got four stupid questions. So,
Okay,
here we go.
here we
So
go.
my first, they're gonna sound random. So my
Good.
first one is radioactivity calculated by way of exponential growth and decay? Is that how we calculate radioactivity?
Uh, okay. Uh, what we have, I'm not sure. It is. I think that uh, there is a probability that a given the given atom will decay, and that probability is given by a number called the half-life. You've
Okay.
heard that term, right?
Yes.
Okay. So
Is that what
uh,
like the half the protons of the half the atomic mass of the atom?
the half-life is the the time you have to wait for half of the atoms of that nature to uh, decay.
Okay.
So when half the atoms are gone, that time is called a half-life.
Got you. So
And
it's
then
all
if you
about
wait an equal amount of
okay.
time, you'll have a quarter. And if you
Got
wait
you.
an equal, and then if you do that, if you do that again, you'll have an eighth, and
Got
so on. Uh, and so uh, so that is what you're getting. The curve of, if you will, the amount of stuff you've got left is not uh, a exponential. I think it is a arithmetic. Uh, it is x to, well, I have to think. I think it through a little bit more carefully, but it's definitely it's an arithmetic, no, a geometric progression where at every given moment in time it progresses by a certain factor down. So is that exponential? I'm not sure, uh, but it is mathematically described by a function that might be exponential. Yes. Okay, I'll go with exponential. Good enough for me at this point.
Okay.
Okay.
Um. So when we when we're so first I'm gonna ask you this pre-question.
Okay.
Going back to I think the last session you had. We were talking about superposition. I delved more into that uh, concept. Um, so when we're
You know, I'm not going to know anything more about superposition now than I did last time, right? So I'm hoping you don't, exceed my knowledge base, but keep going.
well, I've been listening back. I've been listening to you back and learning just
Okay, so
kind
maybe
of
I have
so
something to
you
add.
had tons more than what I had. So
Okay, good.
um, but and I've also done been additional research on top of some of the things that you said. So I've arrived at is that is basically a way of sort of grouping different probabilities of like if we was to use an electron for an example, like different probabilities of that electron state
Okay.
at a certain time, but grouping them all in one kind of soup. Would that be accurate?
Well, in a given atom, we call what's going on inside their electron cloud. So if that's what you're talking about, in a given atom, we have a cloud of electrons. Yeah. Is that what you mean? Or are we talking about something that's beyond the single atom, and we're talking about the soup of electrons in a substance of some sort?
So let's say that we're trying to look at just one electron, like we just want to
Okay,
observe one electron.
okay.
Before we observe it, it is considered to be in superposition, correct?
No, before we observe it, that might be the right word, but I would like to use the word, uh, uh, there's a probability distribution that describes its, its existence. I wouldn't say superposition. Superposition I tend to reserve for things in which there's two things.
Mm.
Uh, but but again, it's not my. So I'll go with superposition if you want, because we haven't gotten to the question.
So so the question that I was going to ask uh, from that is, uh, do we use special operators called quantum operators to determine whether or not something is in superposition?
Something is in superposition.
Yeah, some quantum particle, some object that we're studying.
Um, see, let me back off and say I'm gonna. Uh, sounds good, but I'm now starting to hit my my level of competence. What I do know is that uh, this the quantum state of any object is defined by Schrodinger's equation. Schrodinger's equation can be applied to one or more objects because Schrodinger's equation is, and this is a fun word, linear, which means that you can add it up uh,
Yeah.
and you get, so if you have more than one object you're looking at, you can put them both into Schrodinger's equation and ask what the state of both of them is at any given time, and Schrodinger's equation will give you the probability distribution of where they are and what they're doing at any given time. Once you have given the equation its initial conditions, of which you only know one or the other. You don't know, for example, you don't know the position and velocity at the same time. So
Okay.
if you tell it what its position is, Schrodinger's equation will not know how fast it's going. And if you tell it how fast it's going, it won't know where it is. Uh, but given that you fed the equation one or the other of those two objects, it
Yeah.
will then be able to predict the future of, of what is then possible. Uh, and uh, uh, and that's called the wave solving the wave function equation for
Got
the
you.
position of the particles. Uh,
Okay.
but I didn't use the word superposition there, okay? Because the word superposition to me means that two things are created in such a way that they share a wave function, and that as long as they are in fact described by the equation, they continue to solve to share the wave function equation until one of them is in fact seen by an observer, at which time point
Okay.
you collapse the wave function because you are no longer it's no longer probability, it's in fact reality.
So this superposition, does it imply quantum entanglement?
The word superposition tends to, in my world, which is not too much far removed from your world, means superposition quantum entanglement. Yes, I seem to hear those words together. They
Okay.
mean similar things. But again, I'm not a quantum expert here. This is I'm feeling the burn here. You are asking questions right at the level of my ability to feel comfortable. Okay?
Okay. All right. Well, you gave me a lot, a wealth of information, and I pray knowledge soon. Um, so uh, so now I'm about to kind of go to math. I have a math question.
Okay.
Um, so I have Newton's force gravity equation
Okay.
in my head right now as I'm
Okay.
thinking about what I'm about to say. Some
Okay.
forward questions. So
Right. Right.
Newton's gravitational force is considered a vector,
Right.
but all of the other, so on the other side of the equal side,
Yeah.
all of those quantities are scalars, correct?
That is correct,
So,
except for one thing, right? One thing, it's the, the 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 force of gravity in Newton stuff is a vector whose whose magnitude is equal to the equation you're thinking of.
oh, it's magnitude.
The magnitude of the vector is the equation you're thinking of. But in fact, so when you draw the arrow, okay, that indicates the force, you also need to label the arrow with the magnitude, which, given that you know all the quantities, you know G, big G, small m, big M, R squared, you know all those things, you can put a number on it. I had a person who worked with me, I was just tutoring her in physics, and she kept plugging the numbers in. As soon as she saw what the numbers were, she put them in. I said, no, 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 don't do that. Leave the variables. Don't plug them in into the very end. That's an exercise left unnecessarily, just if you need a final answer on the exam. But don't plug the numbers in, for God's sakes. But she kept doing it, and ultimately I said, you know what? You should not be a physicist. You should be an accountant. and she is to this day. But if you want, you can write a number right next to the vector, okay? And that's all it is. It's a size. It's a number. It refers to the force. It has a force which has a magnitude and a direction, and the force is measured in whatever you like, newtons, pounds, okay, either one. Uh, so, what was your question?
Um, so my question was going to be: does this mean that uh, scalars, the different ways that we express scalars can create vectors?
I didn't. I wouldn't say that so much. But yeah, I guess you said it. Uh, but it's like uh, it's like saying the ingredients can create the omelet. Sure, but I'm not sure that that's useful.
Has
I mean,
are there any
a vector is both a direction and a magnitude.
and the
That's it.
magnitude?
That's what it is. It has a direction and a magnitude. Those are the two qualities of a vector. And you have to have both the scalar part and there's things called unit vectors. So if
Mm-hmm.
you want to play, if you want a building block instead of Legos, you go out and you buy a set of unit vectors, okay?
Yeah.
And they all have a magnitude of one, okay?
Mm.
And then you can multiply them by any number you want to give them a magnitude, right? They start out with one, so if you multiply it by whatever magnitude, you get the magnitude. So yes, you can start with uh, uh, scalars for numbers and vectors for building blocks. Yes,
I got you. All right, and I got one more question.
yeah, these are good questions, actually.
Thank you. I got flashcards, man. I've been in the rabbit holes.
Uh,
um, uh, what branch of science is nuclear notation uh, and Broadcat notation? So these are two math kind of styles of math that I've been coming across as of recent.
okay,
But I'm
I'm gonna.
not. I kind of get conflated when I'm in
Yeah,
my
the second
explorations.
word I've never heard before, and the first word just has the word nuclear in it, so I'm not sure I know that either. Uh, and the word notation is fun, but I'm not sure what you mean.
So that's not something that you're familiar. That's not those aren't terms that you're familiar with at
No, that
all.
doesn't mean, of course, they don't exist. You've seen them, so of course they do, uh, but I'm not familiar with them. The way that I mean, like for instance, give me an example so maybe I can understand a little bit.
So I'll give you the context that I've seen them in.
Okay,
So
good.
nuclear notation, or well, the way that I'm associating them.
Yes.
Nuclear notation, I've seen them when I'm studying things like nuclear fusion, um,
Okay.
nuclear fission, the
Right.
whole nuclear uh, physics
Right.
and radioactivity realm. I don't know what that is, but the
Okay.
Brocket notation is when I'm looking into superposition, like the realm of superposition and then wave functions and things like that. So,
So I definitely can tell you that you are above my pay grade at this point. Let me spell Broquette. B R
so it's BRA hyphen KET.
B R A uh, hyphen A what?
K,
Oh, K E
like
T.
Kappa.
It's funny. As soon as I put the thing in, it says Broquette. Broquette notation is Dirac notation is the notation for linear algebra and linear operators or complex vector spaces together with it. Okay, let me see what this looks like. Yeah. Okay. Uh-huh. Yes, so this is getting into mathematics that I did not take. Okay, and it's under the subject of quantum mechanics. So I'm in this place on Wikipedia. Said Brocket notation. The first topic that comes up is quantum mechanics, uh, and the ket is. I've seen the ket and I've seen the bra. I've seen them both together, and I have seen the whole equations before, and I've seen all of this stuff before. But in fact, uh, I really, if I was, and I see the equations now, I am literally not able to interpret the equations or read them to you, whereas you could read them to me. I'm saying ket. I'm seeing the first one. Ket of A equals the ket of B plus the ket of C. And it's all sorts of cool stuff, and it's exciting to me to see stuff I don't know in an area that I essentially did not study in school. I almost got to this, but I didn't. So thank you for finding me something that I literally don't have a clue about. This is cool. This is cool. That's good. I actually like that as a process, and I'm happy to see that stuff in my life because it reminds me how little I actually do know about the stuff that I think I know something about, and that's good for me.
Well, thank you for answering my questions, Dr. Laird. You're always giving me a wealth of
Yeah, but
knowledge
now
covered.
I'm curious as to why are you studying that? What course are you taking that would be important to you?
This is pure passion, man. It's no,
Really?
yeah, it's no specific reason. It's pure passion.
Are you in? I forget. Are you in school studying this stuff? I forget.
No, I'm not. So the only thing that I'm professionally doing is technology. I work in data analysis.
Right. And that's what I thought. Yeah. That's cool. Uh, this is what what Dash is talking about is what I would call intermediate quantum mechanics for sure. I haven't taken intermediate quantum mechanics. I only taken freshman quantum mechanics. It lasted, I think, one term, and then I took nuclear physics, which took one term, uh, and that's really my bottom line experience with, you know, formal education in these things. That's not what I know. So that's, I really, and when I talk about these things, Dash, you are perhaps the expert in the room, not me. Thank you.
Well, I'm just a learner. I'm a student until death.
Well,
So,
but I think you can answer these questions almost better than me when we talk about superposition versus entanglement. I think you're maybe better qualified than me to answer these questions.
well, I do my best. I'll give you that. I do
Okay.
my best.
All right. Well, I mean that you have to understand people in the room. If I do this, and I do have a PhD. That's where the doctor. It should say Dr. Laird, but it's Laird Whitehill, and I do have a PhD. But it was 1972, okay, and and I haven't worked in this field since. I've taught it, for 12 years prior to COVID, but not as an exercise in fun, and let's talk about the universe, shall we, boys and girls? In this case, it was old people, uh, but I've been studying this stuff my whole life, but not at the level that Dash is studying it right now. I've been studying it from the point of view of let's see what I can remember about the universe. And so I say sort of skimming the top. So, for example, that stuff at the top of this room is in fact a story that I'd like to tell. Okay? I'd like to tell a little story that I learned today. Well, I didn't just learn it today, I learned it the other day, and then I decided I would relearn it today so I could talk about it. And this is the level of things that I can talk about, uh, and not the level of things that Dash is talking about. So here's a story. Uh, and I'll tell the story quickly, and then I'll answer questions to those people who didn't understand what I just said, okay? Because I will skip a lot. First of all, the video on the top is by Dr. Becky. She is an astrophysicist, a working astrophysicist, who also spends an awful lot of time creating these videos, which are designed, as far as I'm concerned, for people like me, uh, as well as people like you. But it's so well designed for people like me that I can't imagine that you, the people in the audience, could get as much from it as I can get. She's literally talking to me. Uh, and, and what she said to me is the following. Uh, uh, and she has like 20,000 people who watch this video. So it's like she's not talking to the outer space, the internet. She's talking to knowledgeable people. Anyway, so recently there was headlines that said, uh, the galaxies the origin of the universe, when the universe first was did its Big Bang thing, the universe is like producing these galaxies which are far too big to have been created in the early universe. So maybe there's something wrong with the Big Bang theory. Maybe well, the first thing she does in the video is say, that's ridiculous. There's nothing wrong with the Big Bang theory. What is a problem is we are seeing galaxies that seem to be too massive in the initial universe. That's a problem. Big Bang is not a problem, but this is a problem. Why are we seeing galaxies that are too massive just after the universe was created? Please explain. And she goes ahead and she says, well, uh, it turns out that it's not a problem. We seem to have a good explanation for it. So, this is one of those things that James Webb uh, found a mystery, and within the same year that it found the mystery, we have more or less put the mystery to bed. This is what makes James Webb exciting. Stuff we didn't think was possible, we saw was out there, and we couldn't explain it. Now we can. So, what's the explanation for this? So, uh, the idea of a massive galaxy. See, you can't tell the mass of a galaxy. Uh, there's no way to measure the mass of a galaxy. Well, there is. If a galaxy has a certain brightness, well, then it's also a certain mass. And if it's brighter, well, then it's more massive. And if it's not as bright, then it's less massive. That's a rule. And how do we know the rule is true? Because we can investigate the nearby neighborhood that we live in with thousands and tens of thousands of galaxies. Remember, the universe has trillions. So we can investigate the tens of thousands of galaxies near us, and we come up with a rule that says the brighter, the more massive. Thank you very much. Now, if you use that same rule and you go and you can't see the galaxy except its brightness because it's in the other side of the universe, then the only thing you can see is how bright it is. You can tell how far away it is because this little thing called redshift, which is guaranteed to give you the right number as far as how far away it is. So if you see a certain apparent brightness and you know how far away it is, then you can come up with an absolute brightness. And then you look at the absolute brightness and say, excuse me, how could you get something that bright in the early universe when the universe was just building galaxies? How did you get a galaxy to be as bright as that? Right? How did you do that? How did the universe make something that can't be made in the early universe? Well, it turns out that it didn't. It turns out that we made a mistake. And the mistake we made was that we assumed that the story that we are telling ourselves about the galaxies near us are the same story that we see in galaxies far away. There's an assumption that we have validated in our nearby neighborhood, and it's called the initial mass function, which I will not explain except if asked. Uh, and and we have gone so far down the rabbit hole, we have decided it's a universal initial mass function, and then we take it, we apply it to the galaxy that we saw on the other end of the universe, and it turns out that the galaxy is too bright. However, all we have to do is change the initial mass function assumption from being universal, which it's apparently not, and just say it depends upon when the galaxy is being created. Maybe the initial mass function is different, and that essentially refers to the the distribution of sizes of stars, whether there's more big ones created or small ones created. That's what that initial mass function means. And if we change the distribution of masses, then nothing's a problem anymore. So that's it. change the initial mass function, and the galaxy stops being as bright as it seems to be. It's no longer that bright because we are making assumptions that we don't make anymore. So that's what you can learn from watching that video. Uh, and I'll be happy to answer any questions about that or any other questions that you have. This is a new, by the way, James, this is a new tactic. I have never, if you're still there, I have never done this before in this room. In the 3 years that I have done this room, I've never lectured on a topic before without getting a question about it. It's the first time. And it's something I could do in the future if I had a YouTube. What I would do is I would wait until there was an audience like the number of people who are here now, and then I would deliver the lecture on the topic that I had previously studied up on, like it was a class. But you people have come to ask and hear the answers to questions. There aren't as many questions as there used to be in this room, so I've decided to take it upon myself to lecture about something that you didn't ask a question about. But I still would be happy to answer any questions because that's the way the room works best for me. I am not happy to just lecture on things that I don't know if it's interesting to you. Anyway, so with
Well,
that, yes.
this is Zia, and I'm glad that you brought up that little lecture there. And I think it's, yeah, I think that adds a dimension to this Ask the Awesome and Stupid Questions segment. So good
Right.
job. And
Right.
I have I'm still curious, Dr. Laird, about um, I'm curious about the pole shifts on the sun
Huh?
and our Earth. I'm still not understanding how that happens, or it like. So I'm curious about how the poles switch their polarity,
Mm-hmm.
and then I think I first thought that the Earth was gonna. I think I thought the Earth was just gonna like spin upside down, and exactly.
Right. Right.
Yeah, that's
But
yeah.
it's interesting because, like on the Earth, the poles have shifted, north and south have shifted, right? You know that, and
Yeah.
that's what you're referring to, uh,
Yes.
and that happens, with a time frame of hundreds of thousands to hundreds of millions of years. Now, I think it's, uh, I'm not sure exactly how frequently, but certainly no more frequently than every 100,000 years to
Mm.
maybe a million years, and the poles shift. And on our Earth, the pole is not shifting so much as it's wandering, and it wanders so much that if you were on the Earth and you were following the Earth's pole, the magnetic North Pole around, you'd
Mm-hmm.
need to be in a car to follow it around on the Earth. It moves too quickly, I think, that on the surface of the Earth that it would be hard to
Right.
keep up with it. Or if not, then it's equally funny to imagine yourself spending all day walking to follow the north magnetic pole of the Earth. That's kind of a funny image in my brain right there. Uh, and but so the thing is, the Earth's magnetic field reverses,
Mm-hmm.
and we know that. How do we know that, Laird? Oh, I'm glad you asked. Uh, the way we know that on the Earth is is that is down the mid-Atlantic ridge where the continents uh, ha- are separating and moving apart from one another at the rate at which your fingernails grow. The mid-Atlantic ridge is where the new material is bubbling up
Mm-hmm.
from the Earth's crust, and when it bubbles up, it is molten, and while it's molten, it can record the magnetic field of the Earth's magnetic field of the Earth as it's molten. But as soon as it solidifies, holding in its grasp the way the magnetic field was at that time of solidification. And so they literally can just dig up cores from the mid-Atlantic ridge and see as a function of time, as function of distance from the ridge, what the magnetic field of the Earth was, and you can literally see it come and go and come and go and come and go, and they can literally tell you, how long ago the last reversal was, and I just don't know what that number is.
I can't remember either. I think the sun is on the 11 year, every 11 years it flips. The
Yes, and
pole,
the sun does it every 11 years.
right.
So the same answer is why the Earth does it every 100,000 years and the sun does it every 11 years, and that I don't know the answer to. And I think the answer is complicated,
Mm.
very extremely complicated in the sense of they they understand it at the level of at some level, but I think it's buried in the differential equation solutions. So in other words, if you need to wave your hands and explain it, which is what you want me to do without even the ability of hands, uh, it's extremely hard to do. Whereas uh, uh, there was one of my professors at Cornell, his name is Tommy Gold, and he came up with a hand waving thing that made him famous, and and I can tell you that one. So he asked and answered the question, why are how does are solar flares produced?
Good question.
And he asked the question. Well, other people had asked the question before him, but he answered it, and he said that that solar flares are produced by uh, there are magnetic fields on the surface of the sun. That's known,
Hmm.
and those magnetic fields constrain where the particles, which is the sun is made of a plasma that's heated to a temperature such that it's ionized and responds entirely to magnetic fields. So if you ever look at the surface of the sun, you can literally see uh, the sun's surface in a granular manner as it responds to the magnetic fields. But sunspots are in fact intense magnetic fields which restrain uh, the uh, uh, the warm gases from coming up from below. So the gases that at the sunspots are in fact darker because it's not as hot. So magnetic fields are the be all and the end all of what's going on in the sun. And he said that the magnetic fields are constraining those protons and electrons and forming paths that they can follow. But he says at some point the magnetic fields break. This is a key word. They break, and they reform into a separate object. In other words, instead of just they crossed, and then some point they rejoin each other in a different way, and they release from their magnetic pull these protons and electrons, which then are free to just fly off.
And that would be
A
the
solar flare.
solar,
Flare.
that would be the something coming at us, and
Right.
it has that Carrington event hit us.
Right.
That was one of those, right?
Right. Now I'm not going there with that, but yes, you're right.
Okay.
But I am using the word solar flare, although Carrington events are coronal mass ejections, which are slightly
Cool.
different from this. Okay, so we're
Thank
talking
you.
about solar
Thank you.
flares here, and really it's an important distinction.
Very
Uh,
important distinction. Thank you. Yes.
but we're talking about solar flares, and those are things that that do eject mass from the sun as well, and they do. Uh,
Mm.
but but what I'm saying is, you can visualize magnetic field lines breaking. Okay, so that works for you, but 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 maybe you can then use that same visualization to imagine that magnetic field lines curl up and then recombine in the opposite direction. Maybe that doesn't work as well for you. It certainly doesn't work as well for me. So I haven't seen a hands waving explanation of that, but I'm sure there are some out there. I just haven't seen one. Uh, but I'm sure there's a good one out there, much better than anything I tried just now.
Well, thank you, my fine feathered friend. I really appreciate the
Thank you. But I would
answers.
really
Yeah.
want to know the answer to your question just as well. I have to thank you. It's,
Mm.
yes, good. And while you were speaking, Lisa, I mean Lois,
Hmm.
there's a Lisa in the room, uh,
Nice.
and
Have her
so
come up.
yeah,
Ask
she's
a
here.
question.
She is here.
Come on up.
Come on up. She's up. She's
Oh,
up already.
great.
So that's good. So and so she's looks like her microphone's off and she's ready to speak. Go, Lisa.
Very cool.
Good. Welcome to the stage, Lisa. Tell us what you're thinking. Now, it's possible that she has stage fright. Ah, here she on bicycle on. Are you here, Lisa? Are you ready? Not ready. Uh-huh. Uh, well, your microphone is ready to speak. So maybe, well, how do we know? What's the problem is? She could have low internet capacity. It's a
Yeah, I was
possibility.
gonna say, Lisa has a pink ticket. Maybe she hasn't been here before. Lisa, your mic is open, but we can't hear you. You could, if you have a glitch, you could leave the room and come back. That would help.
Oh yeah,
Otherwise,
that's been done before. If you
yeah,
can figure out how to leave the room and come back, that sometimes fixes it.
it, there.
She did it. She left.
Yeah.
She's definitely listening. She's definitely listening. That's cool. That's cool. Let's see if she gets her way back. I have, but my personally, I fall out of the room from time to time, and when I do, it takes me minutes to get back. And since she's a newbie, she might take a long time to find her way
Well,
back.
I think if you
Uh,
just swipe left by,
yeah, she's back.
oh,
She's
there
back.
she
Let's
is.
see.
Woohoo!
Okay. Yeah, Lisa,
Hi, can you hear
hi.
me now?
Yes.
Oh, great.
Terrific. Thank
Well,
you. Thank you, Lois. That was perfect. I forgot that. Yes.
yeah, thanks so much, Lois. Hi, Dr. Laird. My name is Lisa.
Hi,
Uh,
Lisa.
this is such a cool group. Um, I know nothing about astronomy, so I have a
Perfect.
very basic question for
Perfect.
you.
Hmm.
Um, So I know, you were talking about the Big Bang Theory earlier, and I'm just curious if there's any speculation or if you have speculation on if it's possible that the universe goes through a series of Big Bangs, ending and beginning again,
Hmm.
and if you think that's a possibility and why or why not, and B, if it is something that is a remote possibility, are there would there be any signs or evidence that we could look for to
Uh,
show that one day the universe would end, or if it has already ended in the past?
but first of all, the bottom line answer to your question is nobody knows. Okay, unfortunately, but that doesn't mean that we aren't checking it out. Okay, so are we looking to see if we can answer your question? The answer is yes. Uh, so the universe, whether it's going to bang again and do the thing where we're just one of many big bangs, depends upon whether or not the universe is expanding or contracting, obviously. And 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 in the past, before we knew much, uh, it was a it was a it was a game of, well, it could be either way. Then Hubble came up with, uh-oh, it's expanding. So that's the story. Then the first question was, oh, well, is it expanding and slowing down? That's the first question you would ask immediately. They asked the question, is it slowing down? So they looked and they took maybe half a century to ask and answer that question. And the answer was, well, no, it doesn't seem to be slowing down. But wait a second, about 20 years ago, they said, excuse me, uh, can I have your attention, everybody? The universe is not slowing down, it's speeding up. And that, boys and girls, took a couple of decades for me to be able to buy it. Because remember, I was born when the universe was just expanding, and who knows if it was slowing down or not. Your question. But uh, so the universe is expanding, and it's accelerating its expansion, and therefore you have this new thing that we all have to deal with now, and it's called dark energy. So not only do we have dark matter, but we've got dark energy. So most of the universe, 95% of it, we don't have a clue about. 70% of it is dark energy, so it rules. Dark matter is, in fact, twice, 5 times more important than matter. So basically, we know nothing about the universe, and and it looks like it's expanding. So the question now is, the first question, since these things are now facts that we know nothing about in terms of why, the next question is your question: is the expansion rate different in the past than it was in it now? And the answer to that question is, it looks like it. Yeah, yeah. The expansion rate was less insistent in the past than it is now. So then the question is, well, in the future, oh, that future is hard to predict, because it happens in the future. Is Will the expansion rate that's accelerating, will that acceleration continue to accelerate at an accelerating rate, or will it decelerate? And that is something we don't know the answer to. And so it literally is possible, given that we don't know what dark energy is. Dark energy could do whatever it wants to do. All we can do is check its history, but we can't check what it's going to do next. So I don't know if the universe is going to contract. If you want to bet, bet I'd give it very low odds that dark energy is going to change its mind and start sucking in on itself. But it's a possibility. Mostly, it's dark energy is going to rip us to shreds, and by the time we're trillions of years into the future, there's nothing left of the universe that can be seen because it's all been separated from one another. So Andromeda, which is 2 million light years away from us, if it remained 2 million light years away from us, a trillion years in the future might in fact be invisible to us because it would be more than it would take more than it would be so far away that light could never reach us because the space had expanded so far that light cannot reach us from the things that are still in the universe but beyond our cosmic horizon. So that's a possibility, and more likely than the one that the universe is going to fall back in and on itself. Yes,
Question
Sal.
about that.
Yes,
Can you hear me?
I do, James.
All right, awesome. Um, I was seeing stuff about how we're in a big bubble of nothing
Yep,
in the universe, like maybe the biggest known bubble of nothing. Is
yep.
that correct?
What you're talking about, a void versus a bubble of nothing.
Sorry, yeah, a void.
A void is, see, the universe has got these little things called voids, and they stretch for hundreds of millions of light years. Uh, so when I say little thing, I'm joking, but the universe is awfully big. So the universe is made up of not hundreds of millions, but you know, tens of billions, 50s of billions of light years. So really, a void is just a space that's it's filled with galaxies, but if it doesn't have the requisite amount of galaxies compared to what we call filaments, then we might say we're in an empty part of the universe.
Low
I
density space.
Low density space. Well, I don't know, James, whether or not it has been said that we live in a void. There are these things called voids and filaments in the universe. They two structures, two types of structures, and when the filaments cross each other, they're often called superclusters. Uh, I don't know that we live in any one of those three things, in the sense of that you may have looked it up and known, but I don't know.
Okay. Because I'll double back on that, but
Okay.
the
But
what I was seeing lately was
but
that like
I actually thought you were talking about, which is fun, and talks to Lisa's question. There is the very non-trivial idea that we live inside of a big black hole, and
no,
that,
but go on, please.
yeah. So it's been said. I don't know how much traction it has, but I like it nonetheless because you see, black holes. You ask the question, well, what happens at the other end of a black hole? Nobody knows, and that's rather disconcerting and unnerving, especially since there's so many of them out there. In fact, the universe seems to have nothing better to do than create black holes, and and it therefore you ask, well, surely the universe could not, and I do tend to anthropomorphize the universe, despite the fact that I don't believe in there's any sort of intelligence, in fact, involved. But I do think the universe should at least not waste its time on creating black holes that don't do anything. I think it would be great if on the other end of black holes there were other little universes, and universes upon universes all the way down. I like that a lot, and I'm happy with it, even if there's no science involved in that. But nevertheless, if you add up uh, the the known radius of the universe, which is 46 billion light years, the 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 rate of the observable universe, that's how far we can see if we are on our best behavior, and and also the mass of the universe, which we can compute because we're very smart these days. And if you put those two numbers together, you come up with a number that exactly works out to be a black hole. Uh, so that's pretty amazing. So maybe we're inside of a black hole, which is perfect.
That's
Uh,
fascinating.
right. So I wouldn't, although I've introduced the subject, and made you all very happy about it, I wouldn't begin to tell you whether there's how much truth there is to that. I do say it's certainly bandied around enough, but whether it's true or not, I can't tell you.
Well, you say so. So it's a known fact that the universe is expanding. What is it expanding into?
Aha, aha!
Like,
I
what is
love
it
that.
filling up?
I love that. Uh, 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 the, I've never been able to get answer that satisfactorily. I can give you the answers that I've given before, but I have to tell you that they won't like one of the answers I think is good, and it's very satisfying. The other one isn't. Okay, so I'm going to give you the satisfying one first, the one that satisfies me. All right, ready? The universe is infinite, so don't bother me. It's not expanding into anything. It is infinite. Now you're left, if you buy that one, with the problem of infinity, but and I've switched up your problem now to imagining infinity instead of what is it expanding into. I like that better, personally. Since why wouldn't, if we're talking about the universe, why shouldn't it be infinite? Right? I mean, you know, instead of having a prime mover, uh, what we had is just an awfully dense moment in time, 13.8 billion years ago, when the infinite universe was compressed a lot, and then it expanded infinitely in all directions. And so I'm happy with that. Now, if you don't like that, let me just ask Lisa, how do you feel about that?
That the universe is infinite.
Yeah,
I I like it. Um, yeah, it sits right with me.
yeah, I like it a lot. I really do. I think it's just it's just so perfect. Given that we don't know the answer to your question, in the sense of what is expanding into, uh, I like it a lot. But let's go with the other possibility, okay? Uh, which you're not going to like. Uh, uh, the uh, space isn't expanding into anything. Space is all there is. So it's somewhat incorrect to ask the question what it's expanding into. Uh, there's nothing beyond space because space is space. And the idea that it's expanding into something creates, you're working with a misconception to begin with. The Big Bang is misnamed. Uh, it was given that name by uh, uh, a person whose job it was, given that he had a different idea, his job was to deride the idea of a space that began at a particular point in time. His theory was the steady state theory of the universe. He and my professor at school, which I mentioned earlier, uh, uh, were the authors of that theory, and he created the term Big Bang to make fun of the idea that space had a beginning. If you change Big Bang to big expansion, then you don't come up quite with the same question. Yes, it's still expanding into anything, but it's simply expanding. So then you can go with, okay, it's expanding. I don't need to have it expanding in. Whereas bang suggests it's exploding into where it wasn't to where it's going. That's what an explosion is. It's here and then it's there. But in an expansion, it's everywhere to begin with, it's just getting bigger. Like, the raisins in a raisin bread are, as the raisin bread cooks and expands, the raisins are moving away from one another, but they're not moving into anything. They are embedded in the raisin bread. So you don't have to ask the question, what is expanding into? It's not as satisfying an answer. Uh, and then if you'd like, we can always go with, well, the universe isn't flat. Uh, and if you go with that, see, the word flat means three-dimensionally, four-dimensionally flat. So basically, we live in a three-dimensional universe which has right angles at 90 degrees, and that's flat. If you were a two-dimensional being, you'd have right angles at 90 degrees, but you'd only entitled to uh, you know create squares, but you're not entitled to make cubes if you're in two-dimensional universe. But if you're living in a three-dimensional universe, it means that you get to have three right angles, not just two. So if you are in a non-flat universe, then the sky's the limit as to what you can do. You can make your universe. Let's use the two-dimensional analogy. Flat paper is a flat universe that we live in, and then you can take the thing and you can create it and make it into a ball. Uh, so then the ball is simply the surface of a balloon, and the balloon is simply expanding. Space is the surface of the balloon, and the balloon is expanding. What into what? It's just expanding. And then you can make it into a torus if you like. You could make it into a saddle if you like. Different versions of this shape of space. But I like space being flat. That's what we know it to be, to the sixth decimal place, or maybe third, I'm not sure, uh, and uh, and infinite as far as I'm concerned. 9 out of 10 cosmologists like infinite.
Hey, I just wanted to mention you said something about a cyclical universe, and if you want to learn more about that,
Yes,
you can look up Roger Penrose, and there's a great interview with him and Lex Friedman on YouTube.
yes. So Roger Penrose is definitely one of those uh, nutcases uh, who have PhDs and also have Nobel prizes that might be worth listening to. But the reason I say nutcases is they they the things that they get their Nobel Prize for are in fact valid. What they speculate, in fact, needs to be taken as speculation. That's all.
I got a cool video put in the little chat area about uh, what a spherical universe looks like in 3D.
Where is that? Oh, you put it in the chat.
It's in the room chat. They also have a hyperbolic universe, but that actually just looks basically normal, but with like more space between stuff. The spherical one's weird.
I'm pressing the spherical one right there. Ah, okay.
Stuff
Okay,
looks
good. I saw it.
bigger as it gets farther away from you, is the crazy thing.
Yeah, I like it. Thank you for posting that there. So James, you're getting the hang of this, aren't you?
I am, and I'm even in a club deck here trying to hook it up to Twitch.
You're
Um,
already working the problem. I don't want to lose the room. I don't see us anymore. Can you hear me?
uh, I can hear you.
Can anybody else hear me?
Yeah.
Yeah, I
Okay.
can
Very
hear you.
fine.
Okay, now I have to find me on my screen. Okay. Because I sometimes fall out of the rooms because I don't know how to work it. So here I'm back. Yay.
Can I ask a follow up question to Lisa's question? Like you said that it took 20 years for you to accept the expansion of the universe is accelerating. What was it that convinced you?
Say again. I'm sorry. Say it again.
Like you said to Lisa that well, you said to us that it took 20 years for you to accept that the universe is accelerating and its expansion. And I was
Yeah.
wondering what was it that finally convinced you?
Well, first of all, I'm skeptical, right?
Yeah.
You can tell me stuff and I won't believe you. And so I need to know where you got your information from. I need to know, So in this case, the people whose information they were talking about, they were using information based upon a very small statistical sample, uh, and like nine, uh, and nine's not good as far as I'm concerned. But people bought into it for reasons that go way beyond nine, and what they were what they saw was there's a so so can I tell you a little story about the universe? Uh, um, Once upon a time, there were things called Cepheid variables, and they told us, and we figured out that uh, that they have a relationship between their brightness and their period. They vary in their brightness according to uh, the bigger the star, the less frequently it changes its period and its brightness and so on. So they could use these as standard candles in distant galaxies, and but at some point they ran out of Cepheid variables because they got too far away, and you couldn't see the Cepheid variables anymore because they were stars, and you can't see stars if you're looking really really far away. So uh, so then we needed another standard candle. So we came up with a standard candle, and this is it. If you drip mass into a white dwarf star, and how do you do that? Because it's got a companion, and the companion sort of drips mass into it. There is a rule of law of nature. Well, actually, it's somebody's rule, Chandrasekhar actually, and he said, if you drip too much mass in, eventually the star is going to explode. So there's a absolute. So what happens is that means that all the stars of a particular type 1A, uh, will always have the same mass when they explode. So they'll always have the same brightness when they explode. So we can use this now as a standard candle. And we've seen hundreds of supernovas explode. In our galaxy, the last one was 400 years ago, but you look at thousands of galaxies, you see them every day, every week or so. And so they have lots of supernovas, and they looked at the brightness of these galaxies, uh, whose distance was known. No, the distance was known by redshift shift, and the brightness was known by saying, type 1A supernova. We know how bright it is absolutely, so we can use the absolute brightness of the supernova, and we can use the distance from uh, the redshift to determine those two things, and they don't match up. It looks like it looks like the universe has been expanding in recent times, where in the past it wasn't. So it looks like recently the universe has been accelerating in its expansion. So they use those things, and if I didn't explain it well enough, that's because I was hurrying through it. But the main point being that we were able to use this these candles, standard candles, type
That's
1A
interesting.
supernovas.
I did not know
I
any.
didn't buy it.
And you said that the last supernova was 400 years ago. Does
Uh,
that mean?
yeah.
But how do we know? Like, if there was a supernova as far as possible as it could be in our galaxy, would we see it?
It
or
might not. We might not if it's behind a cloud. So we expect that there should be one every 100 years on the average because we can do the statistics based upon other galaxies, so we know how often they occur. And if you're a stupid statistician, you would say the following thing: we're due for one.
does that mean we can see them in other galaxies?
Yeah, we can see them all over the place. Uh,
Wow, I did not know that.
right.
We Is there an example like you can visibly see it? Like if there was a picture taken of a
Yeah.
galaxy and there's a supernova, you can see it.
Yeah. For example, the small or large Magellanic Cloud in 19. I think it's 1997. I think it was. I'm not sure. Uh, uh, there was which is a galaxy that is uh, a dwarf galaxy that orbits our own galaxy, the Magellanic Cloud. There's two of them, small and big. It's one of them. There was a supernova that went on nearby, but in not in our galaxy, in the dwarf galaxy, small or large Magellanic Cloud. So yeah, we can see them. Uh,
What is
uh,
this dwarf
what
galaxy? Is that closer than Andromeda?
Yeah, it's like 100,000 light years away instead, or 250,000 light years away instead of 2 million light years away.
Well, when they talk about the closest galaxy, they always mention Andromeda. I never heard
Well,
of this.
it's the closest galaxy of our ilk. There are many more that are closer that, in fact, are uh, small dwarfs.
Oh, this is all news to me.
Yeah, we have a group of galaxies, and we go by the name, and we hang together, and depending upon how you count, we're called the local group. Okay, we 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 we're like the shirts, and the skins. We're the shirts, and there are about 50 of us, or depending how you count, because other ones, you can. It's arbitrary as to, how much. In other words, how many of those galaxies, in fact, are drawn to us versus others. So, Andromeda is bigger than our galaxy, and it's also very much in our local group. Uh, so you have to count a few more galaxies. I don't know how many uh, Andromeda-sized galaxies there are in our local group, but I know there's two, you and us and Andromeda, and then Sculptor is a galaxy, and Large and Small Magellanic Clouds, and I don't know the name of any of the others, but there's a lot of
Yeah,
them.
I always just thought Andromeda was the closest.
No, just that Andromeda is the most famous because it's on a collision course with us. We're pretty sure.
Well,
The
some people say it's already colliding, like we're already.
Yeah, that's a possibility because I mean I see no reason why you should say no. The Milky Way is, by all counts, 100,000 light years in diameter. But hold your horses. It's got a halo, which is possibly 10 times bigger than that, of gases that in fact belong to it, that are gravitationally bound to it, that don't show up too well except by very sensitive instruments. So I'm not exactly sure how big the galaxy is if you count the stuff that belongs to it. I'm just going to make up a number and say a million light years, just to be on the safe side. It could be only a quarter of a million light years.
That's far.
That's far. That's very
I mean,
far.
you can't even comprehend. But the
No,
light
you
takes
can't.
1 million years to get here.
Right. No, you really can't comprehend this stuff. But on
It's
the
hard
other
to
hand,
comprehend the Oort
but
cloud even
but on the
of
other
our
hand,
solar.
think of it this way: although it's incomprehensible, all right, and it is incomprehensible, 100,000 light years across was when the lights from one end of the galaxy is making its way here. We were still a species called sapiens or Homo. You know, when the light started crossing our galaxy. That's a very small amount of time because time is bigger than that. So you got to start going into not into millions and then billions before you start getting into things that are really incomprehensible, even though millions of years are incomprehensible to begin with,
Hmm.
as well as hundreds of thousands of years. All these things are astronomically impossible to understand, you know. And that's why I like to play this game in this room because that helps me understand it. That's
But
really
light
why I'm
is
here.
very fast, and to take a million years to for light, which is extremely fast, that gives you an idea of, well, I mean, that's why it's hard to comprehend the distance
Yeah,
light travels in a million years.
but forget that. The nearest star is too far away for us to even begin to be able to get there. By any technology we can invent with our puny little brains right now, no matter what if you would eliminate the engineering, forget the engineering, just just try to figure out, the how much fuel you need to get there, and what it doesn't work out. It doesn't work out. It takes us, tens of thousands of years to get from here to there. It's not easy to. So light years are ridiculous in its size. Look, not light years, but what about we sent a spacecraft, Voyager. It's out there. It's not even a light month out there. It's only light days out there. And it would have tried.
You're right. Pluto is 4.5 light hours away, right?
I
No, it's
think
not light hour. It's not light hours. It's light days.
it's
It's
like
light
three
days.
days.
No, I think it's closer to 20 light days, something like that.
Oh,
Oh, that's closer.
You got to look it up. I always forget. I know this number again and again. I've said it 1,000 times, but I forget what I've said.
Dr. Laird,
Yes, Lisa.
what are the areas of astronomy research that is like cutting edge and like that you're most interested in these days?
Well, James Webb. Were you here earlier when I'd give a little lecture on what's that thing up on my what I pinned up there, Dr. Becky stuff?
Yes, I think so.
Were you in the room when I was lecturing about it?
I think I caught the end of that.
Okay, so basically, the the cool part about story is that James Webb found something that we didn't expect, created a mystery that was New York Times headline in the science section worthy. Everybody got wind of it who pays attention to this stuff. And then within the same year, scientists figured a way to explain what we were seeing. So mystery found and solved in the same year. That's cool. There are many mysteries that James Webb is creating which have not been solved yet. And so the list is expanding as we speak.
Who is James Webb?
James Webb, he's a guy who helped. He was a NASA administrator uh, who was responsible for creating the telescope that bears his name. Uh, it's a uh, it's the largest telescope that's ever been launched into space. It's 10 times larger in size than the Hubble, and it's sensitive to a different range of wavelengths that the Hubble could not see. And because it's the wavelengths that it's sensitive to are infrared, which can only be seen by things that are very, very cool, because you and I give off infrared, and we would blind the telescope with our heat. And the telescope is interested in seeing things that are extremely cold. So the James Webb is a telescope that is cooled to a temperature that's 10 degrees above absolute zero and is able to see objects in the universe that are equally cold. And since the early universe wasn't cold, but because the space expands, what was hot now became cold as X-rays become infrared rays by the expansion of the universe, and so now the telescope has to look in the infrared to see the early universe, and it's designed to do that, and it's every day it's doing that and finding new stuff.
There was
Even
some
yeah.
objection to naming it James Webb, though.
Oh yeah. I think it's wrongly named personally. It should be named after someone who was uh, a scientist rather than an administrator.
Well, that wasn't the. I think the objection was because he was involved with purging NASA of gay people or something like that.
Oh no, my objection. Yeah, that's the most recent objection, but that came to light fairly recently. I objected because I didn't like the fact that it was named after an administrator.
Hmm.
Uh, but yes, that also be the worst thing. But the thing is that uh, well, yeah, I mean they did it to Columbus. Okay, uh, it's no longer Columbus Day as so much as it's Indigenous Peoples Day, uh, and they did it to all sorts of historical figures. They did it to Teddy Roosevelt at the Museum of Natural History. They took down his statue in the front of the Museum of Natural History because he was standing with a Native American, but at that time an Indian, by his side as he strode upon this massive horse. And it was just too much to take, so they had to take it down. I understand they had to do that, but you know, uh, redacting history is what they did. And
Hmm.
I don't really object. Uh, I think they should have left it up, the statue of Teddy Roosevelt with a sign saying, uh, "Please pardon us, we didn't know." You know. Anyway, well, so
Hello.
what's next? Arif, you have not spoken, and we
Yeah,
skipped you.
I've been listening to
Right,
you.
but you also up on the
No,
stage,
I'm
so
happy to jump in. I
yeah.
do have a question actually. Now, let's say
Well, wait,
you're
Haris, wait. I do want to, and I appreciate you jumping in, but I do want to point out that if Arif doesn't want to speak, it's Hermes
Yeah, I
who
have a
should speak in.
question.
Okay, good.
Thank you. It is really this problem, wormholes, these days were messing me up, and I want to know everything about wormholes. And another question, can we make a wormhole on Earth?
No, so wormholes should mess you up because there's nothing to be said about them except they're very hard to make, impossible as theoretically speaking, unless you happen to have a source of negative energy, which doesn't exist because there's no such thing as negative energy. And so wormholes are more of a theoretical construct, mathematical in nature, but they have no relationship to anything that in reality we could really talk about. So
Ooh,
don't get messed up with wormholes. Find yourself
question.
something else to get messed up about. The
Oh,
universe has a
you're
lot of
saying there is
stuff
no
going on.
wormhole
What?
naturally in the universe.
Yeah.
Why?
Why what? I'm sorry, I missed the question.
Why there is not wormhole naturally?
Wasn't it Einstein that theorized the existence of, or the,
Yeah, the idea if a wormhole would exist, it would collapse instantly. And so if there were such things, they would have disappeared long ago.
Question
So
about.
how can we?
Go on.
Yes.
Oh, sorry. How can we go somewhere else in universe faster than the light speed?
As soon as you know, let me know, okay? Because I don't know. What you no really what you want is an answer to all the questions that we have ever wondered about, and you want me to tell you that, and I won't
Mhm.
because I can't. And all I can say is it makes great science fiction, and you should go there, but don't think about it as being real. It's a story you can tell your children. But when they grow up, they learn that Santa Claus doesn't exist. They will also learn that wormholes don't exist. But in the meantime, you can tell them the story of what you could find on the other end of wormholes. But
Star
Question
Trek Deep
about
Space Nine really messed people up.
yeah, there's nothing
uh,
to it.
Um,
wormholes, negative energy. Oh,
Yeah.
uh, eh, yeah, wormholes, negative energy. If I, the somebody said Star Trek. Alcubierre drive. Uh,
QBR Drive. Yeah, absolutely.
is
Uh,
is like that you have the some amount of vacuum energy in the universe. There was a neat thing I saw about like recently about somebody being able to essentially transport energy via information by knowing when to like pulse energy in and out so that they could suck energy out of a vacuum at a different location by pumping it in somewhere else. Have you seen that?
Well, no, but I have a thing for you. Have you ever heard of? Uh, I'm trying to get the name because my brain doesn't work as well as it used to. Uh, uh, Maxwell's Demon. Have you ever heard of Maxwell's Demon?
Yes.
All right. So Maxwell's Demon was designed by Maxwell of Maxwell's equations, I think, uh, to take a box which has air in it of a certain temperature and a little hole at where the demon stands, and uh, he would sort the molecules that go through. And if it's hot, he lets it go one way, and if it's cold, he lets it go another way, so that as a result, he is able to create a box with one side being cold and one side being hot. which is the opposite of entropy doing just the opposite thing. Entropy increases the disorder, and he has managed to increase the order and he stands there at the door. And so this was given as an example of somebody who could defeat the second law of thermodynamics by this little demon thingy guy. And as it
Yes.
turns out, upon further analysis, people realized that he, the demon himself, using information that he is in fact privy to, uh, increases the overall entropy of the entire system. So, so James, I think, although I don't have not read what you just suggested, I think it falls into the same category. You can't get something for nothing.
Yeah, they basically pump energy, I'm probably butchering some part of this, but like the simplified version is they pump energy into one point in space, and then they use information of what they but the knowledge of what they themselves did to pull it out at another point in space. I put a link in the comments of it, and I'm wondering if like, but that's not, it's sort of negative energy, like it's relative negative energy, but it's not like dipping. It's like if we're at like 2.3 all the time on average and we're dipping down to zero point 0.1, but not like we're going below zero in some absolute sense. But like my question is, there is some positive energy density to the vacuum, right?
Yeah, yeah, that's been said, and I'll buy it because better minds than mine have said it. And so they talk about vacuum energy.
Yeah.
And I don't understand it, but I do like the story about it. Okay, I like
So
this.
so
I
then
like this, the idea that things come in and out of existence at time frames that boggle the mind in terms of its smallness. But go on, James.
Um, so if you pulled the vacuum so that it was like locally less than the vacuum around it, is that kind of quote negative energy density relative to the vacuum? Is that sufficient for things like wormholes or Alcubierre drives, or does that require some kind of like truly absolutely negative energy?
I don't know because you're in realms that I mean I've already said that negative energy isn't real, and then you're saying, well, how about this one as
Yeah,
negative
but you know
energy?
what I mean? Because like kind of negative,
Yeah, well, Uh, I'd
relatively
really
negative.
I would have to say uh, you know more about me on the subject. That's
Eh,
because you have the link in the chat room and I don't because I
fair
haven't read
enough.
it, you know. But
I
it's
have a
Anyway,
fine.
question.
Yes, Lisa.
Um, so, you said just a couple minutes ago, like, nothing can go past the speed of light, wormholes don't exist.
Yeah.
How, what about quantum entanglement and that? Like, is that not faster than the speed of light?
Well, no, because I mean all that business is all very cute and nice and true. Uh, but also, if you ask ChatGPT, which happens to have some points of view on the subject, and so often and can often be right, if you ask, or even Google for that matter, but ChatGPT is more chatty about it all. If you ask ChatGPT whether any information can be transmitted via this entanglement thing, I think it will come up with a resounding no. And so it's nothing can be told to the person at the other end of this superposition. Uh, I cannot tell it what the particle is when I look. I just look. When I look, I know, but I can't say I want to make it such. I can't I can't make it such and then have the other side be the opposite. So I can't send a message. And if I could, uh, then it would be faster than light, but it's not. So there's no real problem here, even though it doesn't make sense. It also quantum mechanics by itself, when you really get down to it, is just so much stuff that doesn't make sense. And you literally with quantum mechanics decide what poison you want to take. No matter what explanation you get, it will never make sense.
It'll never make sense.
I like that.
Right.
All of you thinking of going that quantum mechanics major?
No, that I really like it because there are things that don't make sense because we are small and slow. But we're not small. We're intermediate in size, and the universe is bigger than us and smaller than us, and faster than us and slower than us. And so we only know things that are within our realm. We can know things that are 10 times, not 10 times, 1,000 times, 1,000,000 times bigger than us, 1,000,000 times slower, faster, whatever. But the universe can trump that size, distance, time. Evolution. Guess evolution is something that we can't understand because we're only here for at most 100 years, and none of us seem to have evolved while we've been talking at all, except maybe some of us who got better education than others. But aside from that, nobody's evolved in this room, you know. Uh, and you can't see evolution happening. So forget it. Time scales of our human nature cannot determine or understand anything. We're limited. And yet we think, listen, you're looking out of your eyeballs and you think you're seeing the room you're in, and that's a story being told to you by your brain, and it's lying to you just to keep you happy. Imagine if you saw the room you're in as fragmented as it actually is, because your eyes are only looking in one direction at a time, but you think you're seeing the whole room. Your senses are lying to you. How could you possibly imagine that you could understand anything?
Yeah, you only see a small slice of the electromagnetic spectrum. So if you
And
saw the
then
whole
and then a
spectrum,
small and then a small slice of the electromagnetic spectrum. Your lips can feel heat. That you've been blessed with the ability to sense infrared. But not through your eyes.
hey,
You have
Dr.
no.
Laird,
Yes.
uh, I have a question about the expansion of the universe.
Okay.
And space is expanding. Do you think the fabric of space is stretching to accommodate that expansion, or do you think more space is being produced as it expands?
Um, um, well, more space is being produced as it expands, and the fabric of space is being stretched. The fabric of space is an analogy you've just created out of thin air or thin
Well, it's
space.
something. It's an unknown, though. I mean,
Right,
some.
but you've just used the word fabric of space, and why did you use that word so your little teeny brain could understand that it has curvature, and,
Well,
but
I
but
mean, we know that it bends light,
and
right?
it bends light. So you really need this word fabric in there to help you out. Uh, but I really think it's just just by analogy. I don't think I think they're the same thing. You know what I mean? Stretching.
Well,
Uh, I like the idea of space-time curvature without trying to visualize it because I've been told, and I truly believe what I've been told, that every analogy I've ever seen for the curvature of space-time is wrong. Uh, because uh, the curvature, first of all, space-time is four-dimensional, and what they do is they usually have a big sun sitting in on a piece of neoprene rubber, and they have the planets flying around it as they follow the curve of the neoprene rubber, and that's supposed to work for us as being like the curvature of space-time around the sun, but it's not right. I've
Well, of
seen
course,
once.
but it's a visualization, though. Like it's
I
something that
know,
we
but
can
it's crap.
comprehend.
It's crap. And I have seen one that really tries to deal with the crappy one, to do at least a better one uh, than that one. So there are better visualizations, but we don't really have good ones. that we can do. I mean, have you ever seen a hypercube? No, of course you haven't. All you've ever seen is the shadow of a hypercube on in three-dimensional space. But we
Mm.
can't imagine hypercubes anymore. And
Was
hypercubes are what
is space continuous or discrete, or
is
is it just
space
a relation
continuous or
to objects?
it's been asked recently. Come to my attention. Let me put it that way. It's come to my attention that some people are willing to ask the question: how do we know that there is such a thing as quantum gravity? Maybe we need not to go there. Maybe gravity is not uh, quantized. Maybe everything else in the universe is. Everywhere you look, there's quantum stuff going on. But maybe gravity isn't. And I don't know much more than what I've just said, but I like it. It feels good to me that, first of all, one thing I like about it is we may never know the answer to that. Uh, but we are certainly not going to stop there. We're going to keep working on it. And we may come up with a theory of gravity that doesn't require quantumization of it.
Well,
It's a,
there's
it's,
What?
this guy Stephen. Have you heard of Stephen Wolfram?
uh, yeah, but
Oh
more
dear.
than that, no.
Well, his idea is that space itself can be quantized, and he refers to it as atoms of space, and it's all mathematical, and he's got some interesting ideas.
No, I haven't heard that one. No,
Yeah.
no, no. But see, all this, see, James, let
Sounds like
me,
a
because again,
computer.
I've only known James for less than a week. Okay. Uh, but uh, so he doesn't quite know my motivation for all of this. I am interested in doing this, but ultimately, I'm not the guy who knows the answers to these uh, these marginal things. It tends not to be my interest, which is why I don't know enough about them, because my interest is I want to know what's true before I die. And I don't want, and so don't tell me stories that aren't true yet. Just tell me the facts. Okay? I had a very early idea when I was very young, and that was if I know everything, I'll be happy when I die. I won't mind. That turns out not to have a shred of value. But nevertheless, I've been working that paradigm my entire life, and I'm still going to my grave, just trying to know everything. But I don't want to know the things that aren't true. So that that tends to limit me in my inability to know stuff that other people think that isn't proven.
And how will you know that? How will you know when you know everything?
Well, for one thing, I will never know everything. I kind of learned that very early on. I started out in second grade. I made a list of all the chemical elements in my notebook, figuring out, I'll have a notebook. I'm going to fill it with all the facts. See? So it didn't take me very long to figure out that that was a worthless endeavor. But nevertheless, I became an astronomer based upon the same thought that astronomy is the study of everything. So let me do that. So basically, the goal has never disappeared, but there's no point in pursuing it.
What's the ultimate question that you want answered?
Okay, that's a good one. Oh, okay. Thank you for that. I don't know the answer to that. Let me work on it. Uh, well, from the point of view of the Hitchhiker's Guide to the Galaxy and the joke I tell in my bio, okay, 42 is the answer, but the problem is we don't know what the question is, okay? So that's a joke that's told by Douglas Adams, and you
Mm.
have to have read the books before you begin to understand that. That's funny, uh, but uh, but so uh, but if you reverse that question, because what the bottom line is that everybody seems to be asking in this room, ultimately at some point or another, is what is the purpose? And I always, when you ask me that, I turn it back and says, what's your purpose? But then, and then in the end, I have to say that the universe looks awfully magically perfect. And I can't help but go there myself and myself ask the question, well, was the universe created just so I could be here talking about it? And
Well, I
I don't know
I
the
think
answer to that.
well, you are part of the universe.
Right. But I don't know why it managed to create me because, and I'm very pleased that it did. But I think I will never know whether there's more to it than that. And I'm just very respectful of the fact that it's allowing me, it's created me so I could, the, I think it was Carl Sagan who said, the universe, uh, the universe has created life or intelligence for a way for it to understand itself,
Right.
something like that.
Well,
Yeah,
then
Uh,
we are the result of the universe becoming conscious of itself.
right. The universe needed to make us so we could understand it.
then don't you think, Dr. Laird, that the exploration into consciousness itself is equally as important as astronomy? And have you studied that before, or is that even something science touches?
I'm of the belief. This is me personal now, and you heard here first because I don't know you find it elsewhere. Uh, uh, I believe the study of consciousness is never going to go anywhere. Uh, and that's because, no, really, I'm serious about this. This is my own thing, and I am an outlier for sure. But I can explain what I mean. Uh, the two simple things. One is that how do I know that you're conscious? I don't. I have to take your word for it. Okay. Well, there's it. That's also why because I'm conscious. And so I kind of reason by analogy that you're conscious. So if you tell me you're conscious, I can buy it. If you build something out of parts and it announces that it's conscious and it can perform all the tricks that you can perform and it says it's conscious, how do I know? That's the first trick that I'm using. And the second trick I'm using uh, is there's only one way to know if something is conscious. It's through our communication. I'm communicating with you. You're communicating with me. And the one thing that neither of us are very aware of is the fact we're using words. In the absence of words or symbolic communication of some sort, we cannot discuss consciousness. So, cats, are they conscious? Well, let's ask them. Are you conscious? They can't answer. Why? They're devoid of words. So you can't ask the question of a cat if it's conscious. The only way you can determine if it's conscious is to teach it to speak and then ask it. So that's why those are the two reasons I think we will never answer the question of what is consciousness. We can have all kinds of, of discussions about it, but I don't think we'll ever figure it out.
Well, they might not be able to talk about consciousness, but they communicate vocally, and a cat owner knows the meaning of the different
Yeah, because
vocalization.
he's got words.
Well, no, the cat vocalizes, and the cat owners understand the different vocalizations that
Yeah,
the cat
so
owner
you should
knows.
try to ask a cat if it's conscious. Really, seriously, try that sometime.
Yeah, I
That's what
get
I'm saying. You can't have that conversation with a cat.
right.
Now, maybe you might be able to have a conversation with a whale, but that's because whales have words.
Mm.
If you have word, I'm not saying we're the only species that can have be conscious. I'm saying without symbolic communication, uh, we can't discuss it. That's all.
But there's a difference between communication and having self consciousness.
Say
Like
again?
there's a difference between like communication with another person isn't dependent upon whether or not you have consciousness.
No, but I want to talk it. No, it doesn't. Of course it doesn't. I just want to
Okay.
discuss consciousness with you. Are you
Okay,
conscious, Haris?
very much so.
Okay, there you go. We've solved that problem, but I can't prove it.
And your definition of consciousness, self-awareness?
No,
Where?
whatever. See, I'm not bothering to define it. Thank you very much. I'm not gonna get trapped. I'm not gonna get trapped. I'm just saying I'm conscious. He's conscious. We agree. Okay. Now, given that we have agreed what we're both conscious, let's go ask a third person, maybe the cat, see if it agrees. And when we come to the whale, hopefully one day we'll be able to ask the whale that question. They are beginning to communicate with whales. They have done that recently, a preliminary conversation with a whale. Uh, and so we'll see. But I don't think that's why I don't think consciousness is a worthy thing. Uh,
Well,
uh,
it took us hundreds of years to communicate as well as the whales, because the whales can communicate across the Pacific Ocean.
yeah, that's just a trick of sonar. You know, it's
Yeah.
easy if you have one. So listen. I guess we've exceeded the time limit of this room by as I do that from time to time. I had fun, which is why we went 2.5 hours. Uh, but I should save myself for another time space. But so James, did you see how this works? This is what I this is
Yep,
is this
I
everything
think so.
is
Huh.
this everything I cracked it up to be?
Yeah, it sounds like we should be mirroring audio on Twitch. I've been listening to it through my phone. I don't have feedback or anything, but step one, yay.
Yay. Okay. Well, let's see how so James is going to try to figure out how to get audio and video to get essentially to duplicate what we're doing in this room uh, uh, with essentially the ability to talk to everybody, but for you to see me talk, and for me to be able to talk to you and hear you speak while I am visible. Uh, and that no app out there does that. Uh, and so James, who was introduced to me by a friend as a genius, and I have no reason to believe otherwise, uh, is uh, uh, is going to now apply his genius brain to the subject of whether or not we can pull this off, and we'll see. I've had James, just FYI, have other people in this room suggested the same idea, not necessarily the same execution, but no one has ever actually, to my knowledge, executed this. Otherwise, it would be out there as a thing. It would be. So if you do invent it, maybe we can, make $1 billion out of it. Who knows? Uh, sell it to everyone. Everyone in the world could be talking to everyone in the world. That's a
I mean,
thing.
like it's gonna be like a janky collection of like Twitch and Clubhouse and YouTube. I mean, like maybe if someone can make a central thing for controlling all of that, but like that's a little outside of my like this is gonna be held
No,
together
no, I
like
understand. You're
bubble
not
gum
you're not
and
about to
duct
sit
tape
down
here.
and program a new app. You're just trying to
I
to
mean,
to jury rig a couple of things together. I
yeah,
get
I
it.
mean, like if we got a model, we can talk about it from there, but one step at a
Yeah.
time.
Yeah, right. So this is fun. I had a lot of fun. By the way, my son-in-law Jack has just joined the room. And Jack, Jack always berates me that I don't give him the opportunity to ask a question, and so I will not be victimized. Jack. Do you have a question?
I
I
was
know.
just gonna say that I've seen you talk, and it's not that great. So
Thank you very much.